don't have any idea. You're saying something? Okay, but just I want some feedback whether you can hear me to proceed.
Yes,
We
sir.
can hear you. Okay, great. Thank you. Okay, so now let's move to the operations on vectors. So we defined vectors, we agreed on notation, and we're going to develop some algebra or arithmetic for working with vectors. We start by defining addition, addition of vectors. So if I have two vectors, let's assume I have a vector A. I hope you can see the, going to write with the pencil here or draw with the pencil. So here is one. So I have here two vectors. Can you see it with the pencil? Is it clear?
Yes.
Yeah. All right. So you can see it. Okay. Now here we assume this is vector A and this is vector P. So here we are going to define addition of vectors as follows. This is the tail of vector A, this is the head of vector A, this is the head of vector B, of course. Now, as you see here, we place the head, sorry, the tail of the second vector on the head of the first vector. So as you see here, we have all pointing to the same direction. Then this shortcut here, I'll just try to draw it different color here. This is the vector A plus vector P. Now here, as you know, if I just continue this here, I hope I can get it here right. I don't know whether you studied in geometry at school something called parallelogram. I don't know. Parallelogram, you heard about it? Parallelogram. Okay, so this is a geometric figure where you have it's just similar to a rectangle, similar to a rectangle, but it is the angles are not right angles here. So this is the only difference. So as you see here, the diagonals are different. So they don't have the same magnitude. But here, if these two opposite sides are equal, these two opposite sides are equal. Okay, so you can see here that if you have two vectors, you can span a parallelogram by these vectors, where A plus B is actually the vector connected the tail of the first one with the head of the second one directly. Okay, so this is the addition, and important here, it is a vector. Okay, so A plus B is a vector, so adding two vectors will result in a vector, which means that under addition the set of vectors is closed. Now here, maybe at this point, I'm going to point out the following. I am talking about vectors with the same dimension here. Okay, so A and B are vectors from the same dimension. So if I'm considering vectors in 2 dimensions, they will be having coordinates x and y. So both must be from the same dimension. I can't add a vector of 2 dimension to a vector of 3 dimension, for instance, okay? Because we will see that we will do this component wise. Okay, so any questions regarding this simple arithmetic here? Okay, so next I'm going to list some properties of vector addition. So the first property is so here given, let's start of vectors A, B, and C from the same vector space, same dimension. So there is a vector that if you add it to any vector, you will get the same vector. So this is, if you like, is just the neutral element in the vector space. So it will not affect. Now, how to plot this? This is vector that if you want to plot it, it's just a point, right? It has no direction. It has no magnitude. It's obviously here the magnitude of the vector 0 is 0. So geometrically, this is just a point, and if you add it to any other vector, then it will result in the same vector. So this is the neutral element. Now, if we have a neutral element, we have inverse. You remember the so-called field axioms. We had one of these axioms. So this is the inverse vector. So an inverse of a vector is simply, I hope you still can see it here. Maybe we can just plot it here somewhere. So what does it mean? If I have here a vector, let me just take some, and here is, okay. So if this is the vector A, then this is the vector negative A, okay? So it's a vector that is exactly have the same magnitude but opposite direction. So this is meant with this negative A. Now, if you add these together, you will be having a 0, and this is called the inverse vector or inverse element. Now, if we add two vectors, A plus B equals to B plus A. It doesn't matter the order, so this is what we call the commutative property. So let me maybe illustrate it here. Maybe we can illustrate it on this. I hope you still can see this graph here. So let me just put it here in different. So we said that this is vector P because of the parallelogram property. So this is vector P here. This direction, and this one is the vector A, okay? And as you see here, the vector that connects this point to this point is just the same. So this one is A plus B, and it's at the same time it's B plus A, this diagonal. Okay, if you go this direction, then it's A plus B. If you go that direction, it's B plus A. And it results in the same vector. Now the last property here is the associative property. If I'm adding three vectors, A plus B plus C, so no matter which two I evaluate first, so let's enclose these, then parentheses or these. So this is the associative. This is the associative property. And notice that here, if I am adding, subtraction can be defined as adding a vector so I define A minus B as A plus the inverse of B or negative B. So I'm not going to plot it. I can show you here the graph here. So if this is the vector A and this is vector B, okay? So A minus B is actually A plus minus B, which is this vector here, okay? So here A, this is minus B. If they add them up, you will be getting C, because this one here and that one are parts of the parallelogram. So A, this is A plus minus B will be this vector. Okay, so subtraction is defined as addition of the vector to its negation here. Okay. Any questions so far? Any questions? I try to keep an eye on the chat, but zwei neue Nachrichten, namely no questions. Okay, so let's move further. Now, slowly we are approaching some thing that is different in vectors than in real numbers. Namely, we have different types of multiplications here. So basically, we're going to talk about three types of multiplication. One very simple one and straightforward, multiplying a vector with a scalar. Okay, so multiplication. So here we have three types of multiplication. Of a vector with a constant, which is also called scalar. I think in English they write it with C. Okay, so let A be a vector and K is just a constant real number. Now, what does it mean multiplying a vector with a constant? What does it mean multiplying a vector with a constant? Let's take an example. If so, let me just try to plot this one here. Just roughly so. So This is vector A. This is, so if this is vector A, 2 times vector A is just a vector with the same direction, but double magnitude. Okay, vector with the same direction, double magnitude. While let's say if I just want, while this one here it's minus 2 times A, so it's a vector in a different direction, and so double magnitude, actually same as 2A, but in the difference. So this negative here, it refers to reversing the direction, while this one here, it means doubling the magnitude. Okay, so this is actually the so to speak the informal. Now let's put this in words. So now here we need to distinguish. Okay, so if K is greater than 0, then the result of K multiplied by A is a vector in same direction but with magnitude K times magnitude of A. Okay, while if K is negative, so this is what we demonstrated there actually, then K times A is a vector with opposite direction and K. So magnitude is going to be multiplied by K, while the negative, as I pointed out, since we have negative here, it means the opposite direction. Now here, as you see, in general, even if you are multiplying with a number less than 1, so it's shrinking the magnitude. If you are multiplying with greater than 1, you are just expanding. But the major difference here is that if you have positive or negative constant here, it will affect the position of the vector. Another thing here, maybe at this stage here, you might saw some assignments on the or today, this morning, or yesterday in the second worksheet. So now we said that let's assume let's have vector A, which is part of R3, meaning here that A is equal to, let's say, 2, 1, and 3. Okay. So as you see here, maybe in the worksheet, I listed them in a column or in a row, which notation you use, but let's assume K equals to 5. Okay, then A multiplied by 5 is equal to 5 multiplied by all these coordinates there by the vector itself. And notice here we are going to expand this 5, so we will get a new vector which has the coordinates 10, 5, and 15, for instance, here. Okay, so this is how we multiply with constants. So regardless whether this is like in the worksheet is in one column or in one row, as long as you consider this is the x, the y, and the z, if you are talking about three-dimensional vectors, then you need to expand it. If you have 4, 5, whatever, then you need to expand it to all of the terms representing the vector. Okay, so someone is writing no here. What is no? What is no here? I have no idea. Okay, so you have no questions. Okay, now some properties with this. Let assume we have A and B vectors. Sorry, I read it here in German, but it's a C here, of course. And let's assume H and K are constants. So we'll see how which rules apply if we multiply different. Then multiplying by, for instance, two scalars or two constant. The first rule here is that if I multiply H, K with A, and this is equal to, since bear in mind that H and K are numbers, okay? And we saw that they're real numbers as we assumed here. So the multiplication of real numbers is commutative. So here it means that if I switch the order of the two, it will not affect the outcome. And also if you just multiply it from the right or from the left, it makes no difference. So here A, let's say here HK, it doesn't make any difference. Okay, so this is the first rule. Now what if I have here H plus K and then I multiply it with A? This case, it means I'm expanding A. So here this is equal H multiplied by A plus K multiplied by A. So it's just I'm expanding from the left A to both constants there. Okay, now what if I have a constant and here inside I add two vectors? Again, here we can also expand the constant. So here I can say this is K multiplied by A plus K multiplied by B. Okay. And as we had a neutral element for addition, which is the zero vector, here we have a vector that we call the unit vector, which multiplied by any vector. Sorry, not this is 1. Let me just put it. This is not a vector, this is the number 1. And obviously, this is 1 times A. And it will result in the same vector. So just multiplying by 1 will not change anything. Okay, notice that this is 1 here is a scalar, it's a constant and not a vector. All right, any questions? Okay, no questions. So let's move to the next topic, which is the so-called unit vector of a given vector. So now before that, I will just remind you about how to evaluate the magnitude of a vector. Okay, so given a vector, let's take it in general. Let's call it V, and this is x1. Maybe this is too complicated. Let's take a vector in 3, and it will can be generalized. In general, then the magnitude of V is calculated just as the square root of x squared plus y squared plus z squared. So here, if you have a 4-dimensional vector, then you just square each of the coordinates and put it under the square root. This is the magnitude of the vector. Okay. Now, we define the so-called unit vector of a given vector. Unit vector. Now, as the name indicates here, the unit vector is a vector that has the magnitude or the length 1. Now, out of given any vector, so for any vector, let's say A, actually it's not 0, it's not equal to 0. Then we define the unit vector we will call it E sub A. Now this notation here, you know, in unit in German it's called Einheit, so it's E sub A. It means the vector. The unit vector here may be just of A, okay? Just if you like, as where this vector is, how we get it from a given vector. The unit vector of any vector is simply we divide by the reciprocal of the magnitude of the vector and multiply it by the vector. Okay, so in other words, we are taking so someone is scanning something here. Did you send something here? I can't open it. Hassan. I can't open such files here. So if you just write what you want here. Do you have a question? So we have in the worksheet such questions here or such assignments. So simply this is because of the following actually. Just note why is this called a unit vector? That the magnitude of this vector, of this new vector here, is equal to, this is a constant, so I can take it out here, and then it's the magnitude of A. So as you see here, the magnitude of A, if it's not 0, it's going to cancel and it will be 1. So that's why it's called a unit vector, because it has a length of exactly 1 unit. So wherever you have vector, you want to evaluate the corresponding unit vector. Very simple. Evaluate the magnitude, take its reciprocal, and then multiply it by the vector. So this is the unit vector here, which is a vector, but this one here is just the magnitude, which is a real number, which is 1. Okay, so questions? So if you have a question, just try to type it. Can't open here any documents. Okay, so far we defined vectors. We defined a couple of operations on vectors: addition, subtraction, and multiplying by a scalar, a constant. And we defined the magnitude of a vector. If we take the reciprocal of the magnitude multiplied by a vector, we generate a new vector that we call the unit vector, which is simply dividing or multiplying by the reciprocal 1 over the length of the original vector. So this is a summary of what we did so far. Now we will move to some topic that's, I admit, it's a little bit abstract, but I try just to give you some hint. It's not only abstract, it is it's very fundamental actually in linear algebra. The following topics we will define formally, but before that, let me just give you an informal background about that. In particular, two things: linear combination and linear dependency, or of course independency of vectors. Of course, here both of vectors, okay, corresponding or related to vectors. Now, what is meant with linear combination? Now the term linear means you are multiplying with the vector to power 1. Okay, it's just like when we talk about linear equations. It's equations that involve x, y. They don't have roots, they don't have squares, etc. So it's just like the variable to power 1. And then you can multiply. For instance, a typical example is y equals 2x plus 3, for instance. This is a linear equation. Now here, linear combination, it means you are multiplying with the constant. For instance, I will give you an example of linear combination. If I have two vectors, and then I say that vector u is 3 times vector v plus 2 times another vector, let's call it w. Okay, so this vector here is a linear combination. You see here the vectors, they don't have square roots, squared, whatever, so they have power 1, and here I'm multiplying with constant. So this one, we say u is linear combination of the vectors v and w. Is it clear what is meant with linear combination? Please, these concepts are very fundamental in linear algebra, especially when it comes to evaluating, for instance, or solving linear system. When it comes to later we'll see things like evaluating the inverse of square matrix and so on. This is a fundamental concept here. Okay, linear combination is very simple. You multiply constant with other vectors to get one vector. So we say a linear combination. I give you a very simple example here. Let's assume u equals the 3-dimensional vector 2, 3, and 4. Okay, and v equals the vector 6, 9, and 12. Is V a linear combination of U, or one of them, or V linear combination of V? What do you think? Is one a linear combination of the other? Meaning I can write V equals to some constant times U. Is it possible? Yeah. Obviously, yeah, V equals 3 times U. So in this case, V is a linear combination of U. And also vice versa. Is U linear combination of V? Yes, you can just multiply by 1/3, for instance, to get the vector out of V. Then you multiply 1/3 V to get U. So this is the meaning of linear combination. Now, if you have more vectors, then as in this example here, one vector is a linear combination of two other vectors. And of course, we can expand this to 3, 4, 5, up to n different vectors. I hope that the concept is clear. Is the concept clear here? All right, so let's move now to the next topic that is related. Now, linear dependency or independency. Now, linear dependency and independency can be just proved or shown in linear algebra using different methods. But decisive here is that if you have a linear combination of vectors, and this linear combination is equal to 0, then if the vectors are linear dependent, then the constants, all constants must be equal to 0. Okay? So this is if you like, the formal definition of linear dependency. I don't know whether this must be somewhere here. Okay, so before that, we are going to define some other concept related to the linear combinations. Then we will get back to linear dependency. But as I told you, there are lots of let's say techniques how we can show or prove or disprove linear dependency of given vectors. We will introduce them as we proceed. But for now, if you have linear combinations, if there's a set for a vector space where each vector out of this space can be written as linear combination of the vectors in this set, we call this set a generating system of the vector space. Okay, generating system. So what I'm just mentioned informally, if we have constants, let's assume we have constants k1, k2 up to kn that are ultimately real numbers, and let's assume that we have as many vectors here, u1, u2, u3, and so on up to un. Okay, u sub n. Okay, I have n vectors in constants. Then the vector P is K1 times U1. So this is just a generalization of this is not the generating system. This is, sorry, this is the linear combination definition. Just as the formal definition. Sorry, just correct this. K2 multiplied by U2 and so on is called, so this vector P is called linear combination of the vectors U1, U2, and so on. Okay, it's just the formal definition of linear combination. And now we define, after we define this, the generating system, which is a set of vectors. So let capital S here be the set of vectors U1, U2, UN. Okay. Of course, these are non-zero vectors. Then S, we call S is called generation system or generating system of the vector space if each vector is a linear combination. I admit this is a little bit too abstract, but we will just demonstrate some examples now. If each vector is a linear combination of U1, U2 up to UN. Okay, so this is the general this is the general definition for n-dimensional vectors, but in general we also refer to this set as it's spanning the whole vector space. Is something, some term that's used here in this context, that the vector space here is spanned by these vectors. Now, what does that mean? Let's demonstrate this in 3-dimensional vector space. So let's consider the 3-dimensional vectors. The 3-dimensional vector space is, you can think about it either a triple XYZ, or you can think about it as a column or a row containing three values. So we will agree just to write it in the horizontal form. Of course, as you saw in the worksheet, we can write it in the vertical form. It doesn't matter. Okay. Now we assume here that the vectors E1, E2, E3 are generating system for where what are exactly the values of these vectors. E1 is the vector that has the first components 1 and all others 0. E2 is the vector that has the middle component 1 and the other 0. And E3 is the vector that has first component 0 and the last component is 1. Now here I just refer to these as E because definitely, what is the magnitude of the first vector? Using the formula, square root of 1 squared plus 0 squared plus 0 squared, it's 1. So actually, the three of them are unit vectors. They have exactly one magnitude, but different, let's say, directions. And actually, they are perpendicular to each other. So I try just to maybe at this stage to show you how this looks like. Everyone knows how this three-dimensional. So here we have three axes. So this is, if you like, this is X, this is Y, and this is, let's call it Z. Now the three vectors here, E1 is this vector, which exactly assume this is one unit. So this is E1. This one is E2. And this one is E3. Okay. They are perpendicular to each other. Now, the assumption here is that these three vectors span or generate the whole vector space R cube or R to the power 3 or three-dimensional vector space. Now, if I ask you just give me a vector in this vector space, it's triple, three numbers. Just write any three numbers there as triple. So give me any three numbers. No one is writing. 3, 2, and 2. Okay. So obviously this vector, let's call it U, is 3, 2, 2 is obviously in R3, right? Now the claim here up there is that you can write U as a linear combination of, so simply it's 3 times E1 plus 2 times E2 plus 2 times E3. Let's check it. So 3 times E1 is 1, 0, 0, plus 2 times E2 is 0, 1, 0, sorry, plus 2 times E3, which is 0, 0, and 1, right? So if we expand this, we will have 3, 0, 0, plus 0, 2, 0, plus 0, 0, and 2. Okay, because I expand this, I just multiply it with all components. Now adding up the components of a vector, you add the corresponding coordinates there. So 3 plus 0 plus 0, it will give me 3. 0 plus 2 plus 0, 2. And 0 plus 0 plus 2, 2. Which is equal to U. So actually this will work for any vector. So that's why we call this set of the three vectors that will actually will be used very often here especially in the exercises. We will focus in most of the exercises on the three-dimensional vectors because of the fact that working with four-dimensional, five-dimensional, it's follows the same logic, but then solving the assignments will require too much time. Now working with smaller dimensional, like two-dimensional vectors, is very simple. So that's why many of the assignments will be dealing with this vector space. And before I proceed now, these vectors, they are used in linear algebra and in vector space very often. I saw in literature different, let's say, notations for these. So E1, E2, E3. So these are the unit vectors in the three different dimensions. So E1 is sometimes used as E sub x. This one is E sub y. So referring to the unit vector in x direction, unit vector as you see in this illustration up there, okay? Or E sub z. Now I saw it in other literature. It's just using this x with hat on top of it, y with hat, or whatever. So different notations. So don't get confused. As usual, I tell you to refer to the agreement of the author of the book or the website or the resource you're using to see which one they agreed. And now comes a very interesting, let's say, representation of these, which is I, J, and K. Sometimes with hat on top of it, sometimes without. So I, J, and K. I'm going to use this especially when it comes to evaluating, let's say, the cross product. I don't know. Tell me, are you used to this IJK notation here? Some of you were exposed to this before, so you used it before. So it's very helpful when it comes to evaluating the cross product. They are different, so most of you are familiar with that. So this is the unit vector. Now in some literature books also, you see this vector here, it will be just written as 3i plus 2j plus 2k. Okay, so just to distinguish the coordinates. So this is unit vector. Notice that this notation here, writing this, it's a linear combination. It's a linear combination that we used here, because as we defined it here, E1 is nothing else than 1, 0, 0. E2 is nothing else than 0, 1, 0. E3 is nothing else than 0, 0, 0, 0, 1. So here it's in many literature, it's written as a linear combination already of these unit vectors. Okay, so these three vectors, no matter which notation you are using, do generate the vector space R cube. Okay, or the three-dimensional vector space. Okay, so okay, so just to be consistent with the other group, I just like to define two more topics, and then we can stop there actually. Maybe I can give you some hints for solving the worksheet. So the first thing here is we are going to give a formal definition of the linear independence vectors, which as I told you before, it's a little bit abstract, but nevertheless, to be consistent, let's define it. So linear independence. Of course, here we're talking about vectors. Okay. So given vectors, again, we start with the general case. And of course, all vectors are from the same vector space, U1, U2, okay, up to UN. Okay, these vectors, none of them is equal to 0, okay? None of them, because it will make no sense. Of course, none of them. I is I equals 1, 2, 3. So this is just indicating that none of these vectors is 0. And constants, again, K1, K2. Again, we just take some constants there, as many as the vectors. And these vectors are called linear independent. Let me underline this. If from the fact that I have a linear combination that's equal to 0, let me just put it here, K1 U1 plus K2 U2 plus, if a linear combination is happened to be 0, so this one is equal to 0, then if from this fact it follows that the constants are 0. The constants K1 equals 0, K2 equals 0, Kn equals 0. If from this it follows that this is the case, then the vectors are, oh, we stated this up there, no need to reiterate on that. Okay, so the vectors called linear independent, if a linear combination of these vectors is equal to 0, it forces the constant to be 0 rather than the vectors. Okay, so if this is the case, then the vectors are linear independent. Of course, if this is not the case, otherwise they are linear dependent. Okay, now this is one way to show that the two vectors are linear dependent or independent. We are going to demonstrate this in maybe not this worksheet, in the next worksheet, and also in the next class, how we can find out that vectors are dependents or independents. But as I told you, luckily there are many tools in linear algebra where we can just using, for instance, determinants, or even using the triple product of vectors, where we can much more easily determine whether a bunch of vectors is dependent or linear independent. And again, this concept of vectors being dependent or independent is really a central, let's say, concept in linear algebra, because the conclusion, if given set of vectors is independent or linear independent or independent, is going to have an effect of, as I told you, finding the solution, for instance, for a system of linear equations. If the constants vectors are linear dependent or independent, it will have a big influence of the process of solving a linear system. And it's also equivalently finding, for instance, the inverse of a square matrix. And that's why at this stage I will just, if you want to understand the coming topics better and be able to solve many of the assignments, I just want you to refer to the following determinants topics. Anyone who worked with determinants? So determinants are corresponding to matrices. Okay? What are matrices? What is a matrix? Of n by n matrices. What is a matrix? Anyone can give me an idea what is a matrix? What is a matrix? System. Okay. How is this system organized? Group of systems. So it's arranging values or numbers in which geometric shape it has. Is it circular? It's oval? Is it square? Is it? So in general, a matrix, it has values, right? Let's say A, B, C, D, E, F. So this is GHI. So this is a matrix. Now, we refer to a matrix by its rows and columns. So this one here is a 3 by 3 matrix. So that's why I wrote here n by n. So matrices, of course, can have different number of rows and columns. But this type of matrix, where we have same number of rows and columns, we call them the square matrices. Okay? This is called the square matrix or squared matrix. And related to squared matrices, there was a German mathematician, his name is Leibniz. He introduced a way to calculate a number that determines a real number for each such squared matrix. And this is what is called the determinant of a matrix. So usually we refer to square matrices, parentheses for a matrix. The determinant of this one, for instance, A, B, C, D, E, F, G, H, I, it's just like the absolute value. So changing these into bars. Or sometimes if this is equal, let's say A, this matrix, just you find notation like determinant of A. So it was called determinant because it determines, notice that the output here, this matrix here is a set of 3 by 3 vector space, right? However, this is a real number, so it determines a number for that. And the way it's evaluated, it's using something in mathematics that what we call the recursive, not in mathematics actually, in computer science, the recursive algorithms. I don't know whether you heard about that, recursive algorithms. So algorithm that repeats itself with a lower value. So it's just each step you are typically subtracting one, given a number, for instance, you subtract one in each step, and then you just run a loop until this terminates because it gets to one. A typical example of that, I don't know whether you are familiar to the so-called factorial. You know this notation, n factorial? Have you seen this before, n factorial? It's actually n multiplied by, so as you see here, till we get to 1. And of course here 0 factorial and 1 factorial are initialized to 1. Okay, so as you see here, if you are given any natural number, any let's say non-negative number, then you find the corresponding factorial. Okay, the factorial of a number. So n, if you like, is in W or in the whole numbers. It's not negative number. So you studied this before? I don't see any feedbacks here. No? Anyway, for instance, what is the 4 factorial? Okay, so we multiply 4, subtract 1, 3, subtract another one, next step, subtract, till we get to 1, then we stop and multiply it out, so it will give me 6 times 24. Okay, so factorial, it's actually used in the number theory and probability and statistics very often. And I think I mentioned that when we talked about the when we talked about the power set, I believe, yeah, power set. It's related to combinations and permutations. But anyway, in computer science, it is defined using the so-called recursive algorithm. So for instance, if you want to evaluate the factorial of n, is just like n evaluating the factorial of n minus 1. Okay, then it will, you just run a loop, and then it, for instance, n is not equal to 1. Okay, so as long as n is not equal to 1, you just apply the function is calling itself again and again and again with smaller value until you get to terminate. Okay, so I don't know whether some students were attending. I think I mentioned that today during the tutorial. It's similar to this figure that is I don't know, I think it's Russian, where you have same figure is repeated smaller and smaller, and it's just incubed within each other. Tochka it's called, or something like that. I don't know. So if you want to get to the kernel of that, you need to remove one, then smaller, then smaller, then smaller. This is the case here. Why I mentioned that? Because Leibniz algorithm is similar. Okay. So if you have let's say a matrix where it have 1, 2, 3, 4. I just take numbers 5, 6, 7, 8, 2, 3, 4, 5, whatever. 1, 2, 4, and 2. Okay. So this is obviously a 4 by 4 matrix. So Leibniz algorithm suggests that out of this matrix, we will just take the first column, first row. Okay. Then we will be ending up of having another matrix, which is 3 by 3. From 4 by 4, 3 by 3. Then again, this one, we take this one, and so on until we get to a 2 by 2 matrix. Then we stop there and then we calculate it. If you have a 5 by 5 matrix, but Leibniz here, notice that we need to iterate -1 here. So here you have positive, negative, positive, negative. So please, if you have any, let's say, you haven't heard about matrices before, or determinants in particular, just try to refresh your memories if you know it. If you don't, just try to understand. I will be elaborating on that when we get, maybe next class already, when we get to the cross product of, or the vector product of two vectors, where we will be using this at least 3 by 3 determinant. So please, if you just prepare how to evaluate this, it will be a big assistance. You can Google it. You can just don't make it very complicated. Just go to a small video where it will explain to you how to use it. I will give you a couple of nice methods also in this 3 by 3 matrices. Maybe some of you know it already, how to evaluate the metric, the determinant easily, because it is very, as again, I repeat it, it is very fundamental in the next topics, namely evaluating the cross product. Also, it will be used, I will be giving you formulas how to find out whether vectors are dependent or independent based on the value, the outcome of such determinants. And as I mentioned, solving linear systems is also related very much to this topic. Okay, so let's leave it there. If you have any questions, do you have any questions? If you don't have any questions, we can just stop. And okay, no questions. So just, I wish you a nice afternoon. And again, regarding the tutorial, we will keep it this way. The first session today is tutorial, and the lecture, the next two sessions. Okay. So no questions. Thank you very much and have a nice afternoon. Goodbye. No, for Wednesday, I can, what time of what the lecture? No, the lecture, no, because we have a big group and they have other classes. But the tutorial, if you don't attend on Wednesday, you attend today morning, 8 o'clock, only for the tutorial. Okay. So the tutorial in Wednesday is the last session. Today is the first session. But unfortunately, I can't change the time for Wednesday. Yes, I'm sorry. Yes, I'm sorry, but this is actually the slots that are available. Okay, okay. No worries, no worries. It's not about only that. This is important, of course. Attending and being active, it's something that definitely, if you just concentrate and of course solve the examples we're doing, not be a little bit active, then you will be getting a good grade at the end, hopefully. So good luck everyone and have a nice afternoon. Goodbye.
Goodbye.
Thank you. Goodbye.